Hey everyone. So this is my soda talk that I'm about to give soon, and I figured I'd record a version of it too and put it on YouTube. Yeah, so I'm going to be talking about this paper that's joint with Raghuvansh Saxena, Madhu Sudan, and Santhoshini Velusamy uh, about streaming algorithms for a certain problem called the maximum directed cut problem. So I'm going to start by defining the problem. So this is an example of a constraint satisfaction problem. And the input is a graph, which is a directed graph. It's also a multi-graph, so multiple edges are allowed, multiple copies of the same edge, and n is going to be the number of vertices. So the data associated to such a graph you can think of as just a multi-set of edges, and each edge is an ordered pair of vertices. So an assignment to this graph is a mapping from every vertex to a value of either 0 or 1. And we say the value of the entire assignment x is simply the probability that if I pick a uniformly random edge from the multiset of edges, that x of u is 1 and x of v is 0. So pictorially, this looks like this. So on the left, we have all the vertices that have x equal to 1, and on the right, we have all the vertices that x equal to 0. And as you can see, for this particular graph and this particular assignment, every edge goes from a vertex that's green to a vertex that's blue, a vertex on the left to a vertex on the right. Therefore, this is a perfectly satisfying assignment. So this assignment has value 1. And more generally, it's also sometimes helpful to think about fractional assignments, which assign to real numbers between 0 and 1. And the value of such an assignment is simply the expectation of x of u times 1 minus x of v over a uniformly random edge. And you can see that this is the same as the Boolean definition because Boolean assignments are a special case of fractional assignments. Okay, so what is the maximization version of this problem? So the value of a graph G is simply the value of the maximum value of any assignment. So it doesn't matter if you look at all fractional assignments or only at Boolean assignments. You can see that the best assignment can always be a Boolean assignment without loss of generality by some simple averaging argument. Um, and the algorithmic question we're going to be interested in this talk is, can we approximate the value of a graph given the description of the graph? So there's been a lot of work on this problem in the setting of, polynomial time algorithms. And I'm not going to sort of go through all of them. I just want to mention that, there's some NP hardness results, there's some unique games hardness results, and there's also polynomial time algorithms that are known based on semi-definite programming. Okay, but we're going to be interested in computing the maximum directed cut value in a more simple setting than polynomial time algorithms, namely in the setting of streaming algorithms. So I'm going to show you just a stream of edges, and I want to figure out what the maximum directed cut value is of the corresponding graph. So here are some edges. Okay, that was the list of edges. So this is a slightly rhetorical exercise, but if I tell you the entire graph, maybe you can look at it now and say, oh, this is actually a perfectly satisfiable graph because I can partition the vertices into two sets, and here every edge is going from a green vertex to a blue vertex. But what we're interested in is sort of figuring out ways to approximate the maximum directed cut value of a graph without having to look at the entire graph. So I'm going to talk about this slightly more formally on this slide. Okay, so suppose you have n vertices, and we're going to always assume the number of edges m is polynomial in n. So the input to our algorithm will be an ordered list of edges, which defines the multiset of edges in the graph. So E1 through EM, and each EI is an edge UI, VI, two distinct vertices. And the goal of all of our algorithms is going to be to use sublinear space, and sublinear space in n, the number of vertices, and pass over the list of edges, and then output some v hat, which is an approximation to the value of the graph. So v hat has to be less than the maximum value of any assignment, but not by a factor more than alpha. Okay, and in particular, I want to highlight that the sublinear space requirement is interesting because we're requiring that we use less space than what it takes to store the entire graph. So you can store the entire graph, or at least a sparsifier, once you get to like n polylog n space. So we want to use less than that amount of space, but still get a non-trivial approximation to the value of the graph. And the general plan of all the algorithms we're going to see in this talk is going to be that we're going to somehow, over the course of the stream, sample small pieces of the graph, and then try to infer something about the global max die cut value of the graph only from these small pieces that we're seeing. Okay, so now I'm going to highlight our main results. So for every epsilon, we get a half minus epsilon approximation in a bunch of streaming models. So there's three main models we consider in this paper, and I'm going to go through them one by one. So the first model excuse me, is what happens when we make the additional assumption that the graph's edges are randomly ordered. And by that, I mean that the graph itself is defined by a multi-set of edges. And if I further assume that these edges are appearing in the stream in a uniformly random order, and I am also going to make an additional assumption that the maximum degree of any vertex is a constant, then we get a logarithmic space algorithm. And if I use the same assumptions, except I relax the assumption that the edges are randomly ordered and I allow them to be adversarially ordered, we get an algorithm which is now sublinear space. It's polynomially sublinear space, although it's uses much more space than logarithmic. Finally, if I want to relax this maximum degree assumption and allow unbounded degree vertices in the graph, I can do that and use only logarithmic space, but I have to take a constant number of passes over the graph, which means I don't just see the stream of edges once, I see it a constant number of times. I go through all the edges, then I go through all the edges again, then I go through all the edges again, a constant number of times. Okay, and I want to also mention that in these first two algorithms where we make the maximum degree assumption, removing the maximum degree assumption seems very challenging and is a really interesting open problem. And it turns out that there's several technical sort of ways in which making these maximum degree assumptions simplifies the algorithmic task enough that it seems to become tractable. And I'm going to try to highlight those later in the talk. Okay, so I want to also give a little bit more context about why these results are interesting. So we get these half minus epsilon approximations. Turns out that we know that doing much better seems to be very hard. So there's a few lower bounds in the single pass setting. There's a random space squared and lower bound. There's an adversarial space linear lower bound. And as far as we know, it's very plausible that even if you allow random ordering, and even if you allow, say, constantly many passes as opposed to just one, you still can get a linear space lower bound. This problem appears to be very, very hard. And these lower bounds are all via reductions from max cut. Okay, I also want to mention that we already knew some approximation algorithms for this problem, but the approximation factors that we were getting were bounded strictly below 1/2. So this work, we're sort of approaching this 1/2 threshold where we know beating it is very hard, and before we only had algorithms that were strictly below 1/2. Okay. Now I'm going to get into the main technical tool which we use in our work, which is this notion of local algorithms for the maximum directed cut problem. So first, I'm going to talk about this general framework for reducing the problem of approximating the maximum directed cut value in a graph to estimating the value of a certain assignment. So suppose we know that there's some algorithm A and it produces a good assignment X. So the value of X is at least alpha times the value of the best possible assignment. So then if we're trying to alpha approximate the value of G, it suffices instead to just simulate A. So we could just directly estimate the value of the algorithm, the value of the assignment produced by the algorithm. So we're reducing from trying to do this sort of general task, approximating the maximum over many assignments to estimating the value of a specific assignment. And in particular, since the value of this assignment X is just the expected value of X of U times 1 minus X of V over uniformly random UV, we can instead just estimate this joint distribution of X of U and X of V, where U and V is a randomly chosen edge in the graph. And these are the types of algorithms we're going to be interested in this talk. And specifically, the types of algorithms we want to simulate are local algorithms. And in order to define them, I have to tell you what the neighborhood of a vertex is in a directed graph. So define the radius L ball around a vertex V as follows. It's just all vertices that are reachable via undirected paths of length at most L. Okay, now I'm going to define the quote-unquote radius L neighborhood type of a vertex V as the induced subgraph of the vertex on this ball, the induced subgraph of the graph on this ball, and it's only going to be defined up to isomorphism, meaning I sort of forget the labels of the vertices with respect to the global graph, and I only remember them with respect to this neighborhood. So what this means concretely is something like the following. So here, let me move my little icon. So I have a graph here, G. This is the same graph we saw before, and we're going to use it as a running example. And I've designated a specific vertex V, which is vertex 4. Okay, so, excuse me. Okay, so if I want to look at the radius 0 neighborhood type of this vertex, there's no other vertices besides the vertex itself that are within distance 0 to the vertex. So it's just a single vertex. Okay, if I look at the radius 1 neighborhood type of this vertex V, So if you look at the ball of radius 1 around vertex V, it also includes vertex 2. So the neighborhood type out to radius 1 of this vertex is just, I start with a vertex and then I have a single edge going out to another vertex. If I look at the radius 2 neighborhood, you can see that the radius 2 ball around vertex 4 contains 2, but also contains vertex 6. So if I add on vertex 6, I now get the neighborhood type to be, I start at the vertex, I go to another vertex, and then that new vertex also has another edge coming into it. And you can see that we've enumerated the entire sort of weak connected component containing this vertex 4. So adding additional hops, making the radius larger than 2, I'll still get the same neighborhood type. Okay, so what is a local algorithm? Okay, let me move me back. So a local algorithm is simply an algorithm which assigns every vertex based only on its neighborhood type. So x of v is just some function of the neighborhood of v out to radius L. And it's known via this work from about 10 years ago that good local algorithms for the maximum directed cut problem exist. And I'm going to talk about this more in a few slides. But what this means is that our main goal in this talk is to somehow simulate the behavior of these local algorithms. So we have these local algorithms and we just want to estimate the value of the assignment that they produce. And that's enough to get a half approximation or a half minus epsilon approximation to the value. Although actually it turns out what simulate means is a bit more subtle than it might sound. So the sort of easy case and is one of the places where having a maximum degree assumption is very helpful. So suppose the maximum degree in our graph is a constant. Okay, the radius we're interested in, L, will also always be a constant, although how large L is will turn out to affect how good the epsilon is, how close the approximation factor is to 1/2. So the key fact about having a bounded radius and bounded degree neighborhood is that the number of distinct vertices in the neighborhood is a constant. It's exponential, but it's a constant because both the degree and the radius are constants. And in particular, it fits within the space bound. And there are only constantly many possible isomorphism types for the neighborhood of any particular vertex. So what this means is that if I look at this distribution n, which is simply pick a random edge uv in the graph, and then look at the neighborhood type of u, and look at the neighborhood type of v, the total support size of this distribution is just a constant. What this means is that a reasonable task is just to design a subroutine to output an estimate for this distribution. And if I can estimate this edge type distribution n, then I can plug it into my local algorithm, estimate the value of the assignment produced by the local algorithm, and therefore approximate the global max die cut value of the graph. Okay, now the more difficult case is when the graph does not have bounded maximum degree. In this case, if you have, say, a star, there can be vertices whose radius 1 neighborhoods still contain all vertices in the graph. Okay, so we can't hope to even write down the radius 1 neighborhood of a vertex in a streaming algorithm. So one of the main contributions of our paper is opening up the local algorithm that was studied before, and we design a variant of this algorithm where instead of needing the entire neighborhood of a vertex, you only need a subsampled neighborhood. This is in some precise sense where you start at the vertex, then you hop to like a random constant size sample of its neighbors, then to a random constant size sample of their neighbors, and so on out to your constant radius L. And actually doing this requires, opening up their algorithm and doing some analysis of the compounding errors. Every additional step, you have errors from sampling bad neighbors, and then you have errors from those neighbors themselves can have errors on their, so you have multiple sources of errors and you have to throw them all together. But this analysis works out. And once we have this analysis, actually getting a multipass algorithm is somehow sort of trivial because we have these multiple hops that we're trying to do. So you just use the first pass to sample some random edges, and then each additional pass, you can just sample random neighbors of the vertices you're already looking at. Maybe you need 2 or 3 passes to do this for each layer, but the radius is constant, and the number of passes you need is linear in the radius. Okay. And I also want to mention that this whole idea based on local algorithms can't do any better than getting a past value approximation ratio 1/2, and this lines up with all of the lower bounds we know in the streaming setting. So you can't do better than a half approximation for die cut. And the reason is the following. Look at this graph. It's a very simple graph. It has 2 vertices and it's a bidirected edge. So this graph has value 1/2. So if I assign, say, the left vertex to 1 and the right vertex to 0, I've satisfied exactly 1/2 of the constraints. But any local cut has value at most 1/4. So in other words, there's sort of an isomorphism or an automorphism of this graph that exchanges the two vertices. So these two vertices look locally the same. And any local algorithm will have to therefore assign these two vertices the same assignment x. So the probability that, the expected value of such a cut is just x times 1 minus x. Um, and that is always less than 1/4. So the optimal algorithm, local algorithm in this case, would just assign both vertices to one with probability 1/2, but this only has value 1/4. Okay. And in the last few minutes of the talk, I want to talk more about this black box simulation and these bounded degree streaming algorithms. So again, in the black box simulation setting, I assume every vertex has a bounded maximum degree, and I want to just try to understand the distribution of, if I pick a random edge UV, what's the neighborhood type of each endpoint? And I want to get a subroutine that estimates this distribution. Okay, and I have two algorithms I'm going to design for this task. One works if the edges are ordered adversarially. It uses polynomially sublinear space, and it uses one pass. And then the second algorithm works in the random ordering setting, and it uses only logarithmic space in one pass. Okay, so what's the adversarial ordering algorithm? So the general plan is I'm going to sample a large but polynomially sublinear set of vertices S, and I'm going to record two, this is before the stream, and then during the stream, I record two types of information. Firstly, I record the induced subgraph on the set of vertices. Second, I record the degree of every vertex in the set. Okay, so I'm going to just show an example, and then I'm not going to actually show any of the analysis, but this should hopefully give some intuition. Okay, so we're going to look at the same graph we had before, and the vertices which are in black are the vertices which are in S. So I'm going to initialize counters for each of their degrees. Okay, then edges are showing up. For instance, this is an edge. It's not in the induced subgraph, but it does contribute to the degree of vertex 1. So I mark that vertex 1 now has degree 1, and so on. Some edges show up and they're irrelevant. Like this edge shows up, it's both in the induced subgraph and it contributes to the degrees of both of its endpoints. Okay, so on. Okay, blah, blah, blah. And now the stream is over. Okay, so what do I know at this point? So I look at some vertices, like for example, vertex 3, and I know that vertex 3 has degree 1 in the graph G, and it has degree 1 in this induced subgraph. So I actually know all of its neighbors. All of its neighbors are in the induced subgraph. Similarly, for vertex 7, it has degree 3, and it has 3 neighbors in the induced subgraph. But these other vertices, vertex 1 and vertex 8, are missing some edges in the induced subgraph. Their degree is higher than their degree in the induced subgraph. What this means is that if you look, for instance, at vertex 3, we know its radius 0 neighborhood type. We, in fact, know its radius 0 neighborhood. We know its radius 1 neighborhood. We actually know its radius 2 neighborhood, but we don't know, for example, its radius 3 neighborhoods, because once we hop out all the way to vertices 1 and 8, we don't know all of their neighbors. And so the general idea here is we can look at this induced subgraph and this degree information. We reject all the vertices whose neighborhoods are incomplete, and then we're left with maybe some edges where we actually know the neighborhoods types of both of their endpoints. Then we have to do some upweighting because there's a high rejection probability, even though it's a constant. There's also correlations between different edges because, like, if one edge and another edge are nearby, like they're connected by short paths, then they're likelier that they'll both be included, that they both won't reject. But this is another place where the maximum degree bound is technically useful. Because it allows us to bound the maximum number of edges that any particular edge is correlated with, if that makes any sense. Okay, secondly, I'm going to talk about the random ordering algorithm quite quickly. So the general plan here is that we greedily collect the neighborhood of the first O of 1 edges in the stream. So I'll just illustrate this by doing it for the first edge. So suppose this is the first edge in the stream. Then more edges are showing up, but as far as I know, this edge, say from 6 to 2, has nothing to do with the edge we've already seen, so I'm just going to forget it. Okay, I'm forgetting edges. Okay, but now an edge shows up which actually does touch one of the endpoints of the first edge in the stream. So now I remember this edge. And I also remember this edge. Okay, the stream is now over. So this first edge that I started with, the edge from 1 to 5, was a random edge in the stream. But I only know I don't necessarily know its entire neighborhood because some edges that went by, they touched vertex 8 or touched vertex 7. but I didn't know that vertex 8 or vertex 7 were in the neighborhoods of vertex 1 or vertex 5. So I didn't record those edges. So I only have a subset of the neighborhood. But the key observation here is due to a paper from about 8 years ago, which says that the distribution of the neighborhood that we actually see is just determined by what the first edge is. So if you condition on what the first randomly sampled edge is, then you're just getting a sample from some distribution depending only on the neighborhood types of that edge. And what this means is that if we repeat this a constant number of times, okay, we have to worry about correlations, and the bounded degree is also helpful there, that we're getting a bunch of samples from sort of conditional distributions on like what the first constant many edges are, and we can use this to reconstruct some estimate of the distribution of actual neighborhood types in the graph. Okay, so yeah, so those are the two algorithms in the bounded degree case. Then we also have this white box algorithm in the unbounded degree case, but it uses multiple passes. Yeah, so those are the main results of the talk. And thank you very much.